So things are a little more involved if we have a secondary reaction that's possible. For example, if we have a weak acid or weak base, we know we can get dissociation in the aqueous phase. So this is an example where we have a weak acid in the aqueous phase, which we want to extract into the organic phase. And so Ka is going to be involved, and it will depend upon the amount of H2O plus that's in the solution. So we can see that if we increase the H2O plus, if we have a lower pH, then by Le Chatelier's principle, we know that the equilibrium will shift towards the reactants. We'll get more HA in the aqueous phase, and that will increase the amount of HA that we get in the organic phase. So if we do a liquid-liquid extraction where we're extracting something which is a weak acid or a weak base, we have another equilibrium involved, and so the distribution ratio no longer will equal the partition coefficient. The first thing we have to do in that situation is calculate the distribution ratio. And distribution ratio for a weak acid is given by the partition coefficient times the hydronium ion concentration divided by the hydronium ion concentration plus the acid dissociation constant. So let's say in this example we have a weak acid with a Ka value of 1.7 times 10 to the minus 5, and we're going to do the extraction at a pH of 5. So if the pH equals 5, the H3O plus concentration is 1 times 10 to the minus pH, so it's 1 times 10 to the minus 5. We can plug those numbers in. We need to know the partition coefficient, and we'll use similar conditions that we used in the last example. So let's say 7.5 for the partition coefficient, and when we plug those numbers in, we get a value for the distribution ratio, which is 7.5 times 1 times 10 to the minus 5 over 1 times 10 to the minus 5 plus the Ka value, which is 1.7 times 10 to the minus 5 and that will give us a value of 2.78. Now we know the distribution ratio, we can plug it into the equation to find extraction efficiency. So let's say we have volume of organic solvent of 50 milliliters and the volume of the aqueous is 30 milliliters, so we're extracting from the aqueous, which is at pH 5, into the organic. We want to know what the extraction efficiency is for that one extraction. So we can find the fraction of the analyte in the aqueous phase, remaining in the aqueous phase, using the equation of the volume of aqueous times distribution rate, or divided by distribution ratio, multiplied by the volume of the organic phase plus the volume of the aqueous phase. This is for one extraction, so we don't take it to the power of n for multiple extractions. So we have everything we need now. We can plug in the fraction of the aqueous phase, which is going to be volume of the aqueous phase, which is 30 milliliters, divided by 2.78, the value of D, times 50, volume of the organic phase, plus 30, the volume of the aqueous phase, and that gives us a value of 0.177. That's the fraction of analyte remaining in the aqueous phase. To find the efficiency, we want to subtract that from 1. That equals 0.822. That's the fraction that is lost, the fraction extracted. Multiply that by 100, we get basically 82% extraction efficiency.